Hi, this is Derek Waters and Adam McGaffin. We're going to be looking at this presentation for the battery management seminar. We're going to be talking about extended power range in USB Type-C and PD 3.1 and the benefits of Type-C with the battery charging solution. Over time, the USB has been adding more power capability to their connector. So if you look at the introduction of USB Type-C alone, that increased the amount of power up to 15 watts, getting 3 amps at 5 volts. Adding power delivery to that Type-C connector can get you up to 100 watts because you can negotiate the voltage up to 20 volts and transfer 5 amps, so you get to 100 watts. So that also really expanded the ecosystem of applications that can be supported with the power over USB. So that's become really prevalent today in a lot of end equipment. But the new topic we'll cover more today is USB PD 3.1, where it's going to be configurable up to 48 volts, still at 5 amps. So that 240 watt limit can open up another set of end equipments that can benefit from the power over USB Type-C. So starting off, just looking back at what the standard power range, or SPR, that's what we call the existing USB PD standard that's been around for several years. If you just look at that, actually the mechanics underneath, it was always capable of negotiating more voltage and current. But there's a Chapter 10 set of power rules that restricts the underlying mechanism for how much power can be delivered over the connector. And those rules are set up kind of like I'm showing here in the diagram, but all around doing less or equal to 100 watts, 20 volt max, 5 amp max. On the chart on the right, you can see at different power levels of the product, if you go vertically, you can see which lines that intersects. That means, and that shows which voltages have to be supported. And as you can see, as you go higher in power, you have to support all the lower voltage, lower power rails. So at 45 watts, for example, that's where you do the blue line and the green line, so all 4 voltages. The thought behind these kinds of rules for the source is to create an ecosystem where the sink knows what to expect from any source it gets connected to. And so with a single number, the customer can understand what the capabilities of the power supply is. That all leads into giving a universal charging interface, something that can be used across many different end equipment. If we turn our attention to greater than 100 watt EPR applications and some of the end equipments that are beginning to adopt that or look into adopting that, one of the first things are the DOCSA monitors, which are intended to charge over a single cable the PCs that get connected. So those we would be doing video over the Type-C and then also delivering power. And along with that is the PCs that need the power, the higher power. So the gaming and mobile workstations today already need more than 100 watts, but we're looking to move away from barrel jacks on those types of platforms. And then even for notebook PCs that don't need 100 watts or more than 100 watts, there's possibilities for charging the battery faster and delivering more power to the peripherals that get connected. So that's a real driving factor in defining this greater than 100 watt extended power range. But beyond the PC markets, there's industrial, where power tools with multiple batteries stacked up together, you have a need for higher voltage, which can be supported from USB-C now. EPOS, which typically needs more than 20 volts, is another application. And then, of course, all the AC/DC chargers that would be used to replace the barrel jacks, those would also need to support the new EPR. Automotive, even today, most implementations are not going up to the 100 watt that's available. So it looks like that'll be further out in time before automotives would be looking at the EPR. Now, if we look a little bit about what EPR is and how it's defined, we can see there's a similar concept. If you look at the table, for different ranges of power, this shows the voltage rails that are required to be supported. So the first one is between 100 and 140 watts. You still have to support all of the 5, 9, 15, 20 volt rails from the SPR region at the required current, and then you're adding a 28 volt rail on top of that. So it looks just like a 100 watt charger for the lower voltage rails, and then you add the higher voltage rail on top of that. Now, on the far right corner, this is AVS, adjustable voltage supply. That's a new thing added in EPR. And what it is that basically you have to be able to supply a voltage in 100 millivolt steps, starting at 15 volts up to your maximum voltage. So in this first power range, that means the AVS supply will be capable of delivering the current from 15 volts up to 28 volts, the current specified by its power rating. So up to 20 volts, it would be able to do 5 amps from 15 to 20 volts, for example. And then up to 28 volts, it's the power divided by 28. So it depends on what your declared PDP is. One of the real, motivating factors behind adding this AVS option is to avoid the case where a particular end equipment or a particular product that needs a specific voltage, that they would need to go and create a new AC/DC adapter just because they need, let's say, 26 volts for their particular product. So again, I'm trying to build a USB-C ecosystem that could be universal in nature. So we don't want to have one-off products that need one specific voltage requiring their own special adapter. We want those to be able to work from any off-the-shelf USB PD adapter. So in this case, any voltage between 15 and 28 volts could be negotiated using AVS. Now, for even higher power adapters, you have the 140 to 180 watt bucket, and then up to 240 watt bucket. So you see the only difference there is you add the 36 volt and then the 48 volt rail on top of the voltages that are already being supported. And this chart just kind of shows the different types of supplies and then the voltage rails that are supported for different power ratings in the x-axis. So you can see on the below 100 watt, there's the programmable power supply, or PPS, which is 20 millivolt steps from the 3.3 volt level up to the maximum voltage, depending on your power, right? And then in the greater than 100 watt region, there's the AVS. So that goes from 15 volts, like I said in the previous slide, up to your maximum EPR voltage in 100 millivolt steps. And then the red lines represent all the fixed supply rails that are required for the different power levels. If you look at how much current's required, it's really just a function of your PDP rating divided by the voltage for most cases. There is also a 5 amp max that is enforced. And then, of course, your cable, which is connected, might not be able to do more than 3 amps. That would also be limiting. And then, even though a supply might be capable of doing more than 3 amps on the lower voltage supplies, it's not required. So for 5, 9, 15 volt rails, the source may only give you 3 amps. There are still some optional things allowed at this point where you could provide more current than required for a given voltage. And in the SPR region, optional voltages are still allowed at this point. So this slide is kind of contrasts different types of supplies. There's a PPS, AVS, and fixed supplies. And just highlighting a few of the things that are different here. I won't go through the full list, but at the top line, there are 2 different brands of chargers from USB logo point of view, a fast charger and a charger. And the key difference there is the PPS. Adding the PPS moves it into the fast charger category. If EPR supported, then the AVS I mentioned is required. It's not optional. So I want to highlight that again. And then the minimum voltage is a big difference. So PPS goes down to 3.3 volts. Of course, the maximum voltage is the key thing. So I've listed those again here. One thing to note is the voltage tolerance across all different supply types is the same. It's just a matter of the precision in the steps may be different, but the tolerance is the same across the board. And then the key thing that makes PPS really different from the other two is the ability to dynamically switch between constant current and constant voltage mode. So that's another thing I wanted to highlight here. Now, moving above the 100-watt level does bring some implications for product safety that need to be considered. The new requirements are all around avoiding fire hazards in the products. If you look at the SPR region, which was, of course, you could do more than 15 watts for more than 3 seconds, which that puts it into a power source class 2 category in terms of product safety. Now, EPR, it's going to cross the boundary of 100 watts for more than 5 seconds. That pushes it into the next category of the PS3 in terms of product safety. And that brings some new things. First of all, it requires a slow burning type of material or the performance equivalent in the product, which is an extra cost, extra burden on the product that needs to be taken care of. The other thing is there needs to be additional safeguards, because if you look at a USB-C cable, there's nothing to prevent you connecting an EPR source to any legacy sink out there, which would only be a PS2 class device. So the good thing is the USB Power Delivery Protocol takes care of all these additional safeguards automatically. Entering the EPR mode uses some new messages, multiple new messages in order to enter that mode, and that prevents a PS2 sink from erroneously negotiating higher power, higher than 100 watts. Because the legacy sink won't understand these new messages that are created specifically for entering EPR mode. There's also a cable check every time you enter the EPR mode, and there's periodic keep alive messages that protect against some fault scenarios, or extra protection against fault scenarios. Okay, so besides the fire hazard, there's also electric shock safety consideration. And in terms of that, the ES1 class device requires less than 60 volts DC. So looking at USB-C, there's a 48 volt nominal VBus. The expected maximum DC voltage is 50.4 volts per the standard. So that gives plenty of tolerance and allowance, even in fault conditions, to remain below the 60 volt level. This is another slide just highlighting in a little bit more detail the process of entering EPR mode and how there are new messages, the new bit fills or even new messages added throughout this procedure, a total of 5 different checks, so that something that's not built to be EPR capable could not accidentally fall into an EPR contract. So I wanted to go into even a little bit more detail about the maximum VBus voltage that's expected in different situations. So on the table here, I'm showing the nominal VBus voltage. So I just started with 20, not looking at the lower voltages, and then up to 48. And if you look at the allowed tolerances, the maximum VBus that you would expect to see in any situation. Now, there's another threshold here, a lower voltage threshold, and that's what's used to detect when a disconnect occurs. So the key thing here, if you follow the diagram, the red line would be the VBus voltage at the sink, and the black line is the VBus voltage at the end of the plug. So while the plug is attached, they're the same. Once you start to unplug from the receptacle, then at some point the VBus contacts break. There's no more current flowing, so the voltage at the end of the plug will rise since there's no IR drop across the cable anymore, and the voltage at the VBus sink will start to fall, assuming the sink is continuing to draw power. Once this voltage gap reaches a certain level, or I should say the absolute voltage on the sink side reaches a certain level, then that's how all USB-C sinks, they're all required to use that threshold as a way of knowing that the plug was removed. So that threshold, the plug removal threshold, is listed here in that row. Now, of course, once the sync has detected that the cable is unplugged, it could take some action to reduce load, turn off the battery charger, or things like that. So the voltage on the sync side would start to go down slower. Now, there is a phenomenon as the contacts in the receptacle and plug slide across each other. There's a phenomenon called fretting, which could temporarily lead to a disconnect of the contacts and then a quick reconnect. So if I'm looking at the very worst case, if the VBus at the sync side has discharged by a certain amount, say delta V, and the plug has risen up to that point, then once they reconnect, there will be a voltage ringing that occurs up to 2 times the delta V. So you would see a peak here. So I've calculated out the peak value in this scenario of how high it could go. And you can see, even at this type of situation, it's remaining below the 60-volt level for the safety considerations. Now, there are other things to consider as far as protecting your system from such a peak voltage. Of course, you could increase the voltage tolerance of everything in the system. That's one approach. Something else we recommend is using TVS dampening solutions. Depending on your maximum voltage, there's different options I'm showing here. And that will very effectively clamp that voltage and at a certain level, depending on the device. Also, something that TI's PD controllers do and help in this regard is to look not only at the VBus voltages for disconnect, but also at the CC voltages on the plug. And the CC voltages will break before the VBus contacts break and can give an early warning to help prevent so much discharge on the VBus line during disconnect. So with that, Adam's going to talk more about the benefits of using Type-C with a battery charger solution.
Great, thanks, Derek. Yeah, so like Derek said, the rest of this presentation, I'm just going to walk through pairing a Type-C and Type-C PD solution with the battery charger, and kind of some of the benefits that this can bring to an existing platform. So I know that Derek kind of talked through the new EPR voltage ranges, which I'll touch on at the end. But for today's discussion, I'm going to focus on this kind of high-level Type-C PD controller plus battery charger architecture, and the solutions that TI has from a PD controller as well as a battery charger standpoint, as well as a reference design that we have that implements this topology. So when it comes to portable battery-powered solutions that implement a Type-C port, there are multiple different architectures you can implement. But the one shown on the screen is the most flexible and robust, depending on your system needs. So first, having a full PD controller, it's capable of negotiating the full 5 to 20 volt SPR voltage range values, and then a buck boost battery charger that's capable of handling 1 to 4 cells and 5 amps of charge current. So this kind of two solution combination is the most robust, and give some explanation and reasons why. So looking at the PD controller, it's the TPS25750D, and there are multiple benefits to this device, but the main one you can see on the screen is just a level of integration that this has, specifically from a power path perspective. So you can see in the block diagram that it implements a 5-volt source only load switch, as well as a 5 to 20 volt bidirectional power path that's capable of handling up to 5 amps of current. Other benefits are the ease of use from a firmware standpoint. So if this is your first or multiple implementation from a Type-C PD perspective, our solution makes it easy without requiring the use of needing to implement a custom firmware solution. We have an easy-to-use GUI tool, which I'll go over at the end, that makes transitioning to Type-C easy and straightforward. And then the other benefit that that pairs with the battery charger itself is this device has the capability of controlling certain TI battery chargers so that there is no external MCU requirement. And so this is taking another look at the benefits and the level of integration that the TPS-25750D has compared to competitor solutions. Once again, the main value add is the power path integration, as well as other requirements such as a dead battery LDO, VCON, if you also want to implement data, and BC 1.2 charging if you want to also support proprietary charging modes. Now for the battery charger we'll be focusing on is the BQ25790. And the ones, there are many benefits of this battery charger, but the ones that I'll focus on are the integrated input current sensing circuitry, so no external current sensing circuitry is required, and then the level of MOSFET integration. So this is a fully integrated buck boost battery charger, and all four of the high side and low side FETs are implemented. So from the buck boost standpoint, the only external component that's needing is the switching inductor itself. So that's four FETs that are pulled together or pulled into this device. And then the fifth one is the battery isolation FET, so the BAT FET, allowing for 5 FETs to be pulled into this device. So now pairing the two. And so this is a reference design that's orderable on TI.com. And this is its name here, the USB PD charge EVM. And this effectively pairs the TPS-25750 with the BQ25790. And so you can see the level of power path integration from the 2 FETs with the TPS-25750 and the 5 FETs with the BQ device. So one common question is, why do I need the power path of the TPS-25750 if it's only going to the battery charger? The answer to that is, in order to be USB compliant, you can only have a maximum of 10 microfarads presented on VBus on the Type-C connector without anything attached. And so this power path effectively isolates the system capacitance and the capacitance that's presented on the Type-C connector. It isolates the two of them so that your device meets that compliance requirement. As far as the communication between the two, the TPS-25750 negotiates to the battery charger using I2C. And all of this information is kind of predetermined based on a configuration that's put in to the GUI, which I'll highlight at the end. So as far as the reference design itself, this right-hand capture is a screenshot of the reference design itself, what it looks like between the two devices, and then on the left-hand side is a scope capture walking through an example of when a 20-volt adapter is connected to this EVM, and a battery charger is connected upstream to the EVM. So walking through the different channels on the scope, the top one is the clock line that is going between the PD controller to the battery charger. The purple channel is the CC pins, and this is the configuration channel, and this is basically the way, the form of communication that PD controllers implement. So it's how this pin is on the actual Type-C connector itself, and it's how one PD controller communicates with the other on either sides of the cable. The yellow channel is the actual V-bus connection, so the voltage being applied on the Type-C connector. And then the green channel is the charge current going to the battery. So reading this from left to right, the first kind of notch is here on the CC pin, and this indicates that the 20-volt adapter has been attached to the EVM, and then shortly thereafter, through that initial connection, 5 volts is provided to the EVM from the adapter. And then from there, kind of in parallel, you see messages being sent on the clock line as well as the CC communication. This is effectively the PD controller negotiating a high voltage contract with the adapter, and then the PD controller conveying that information to the battery charger using the clock and data lines of I2C. Then once that high voltage contract is negotiated, V-bus transitions 20 volts. And then after a period of time, the battery charger actually starts to charge the battery and draw current into the system, which you can see with the charge current. So this is a full buck boost battery charger. And so one question you may be thinking to yourself is, why implement a buck boost charger? And the short answer is it allows your system level of robustness depending on the cell counts, the number of cells you implement within your system, as well as the voltage that's applied on V-bus. And so in this example, the system uses a two-cell implementation with a nominal battery voltage of 8 volts, and 5 volts is presented on V-bus, because once again, the voltage on V-bus can be anywhere from 5 to 20 volts, and then now even go up to 48 volts, as Derek was walking through earlier. So in this example, once your application be able to charge from the 5 volts, so you would boost the 5 volt that is presented on V-bus and boost that to the battery voltage of 8 volts. And then inversely, still using a two-cell application, as if you have 15 volts or even 20 volts presented on V-bus, you'd still want your system to charge from these higher power supplies. And so in this implementation, the battery charger would act in a buck mode, which is 100% controlled by the battery charger itself, the BQ25790. Okay, so how do you configure the PD controller? So mentioned multiple times that the PD controller handles all of this configuration and negotiation, but how does it do this? And so the short answer is through the use of our online GUI tool. And so there are 2 steps when it comes to programming the device. Step 1 is filling out and answering the questions related to the characteristics of the system as a whole. So the source capabilities, sync capabilities, if there's a data role, if there is the preferred data role, vendor ID if you have one, things like this. And then once that information is entered in, you then follow up with the relevant battery charger information. So in today's discussion is focused on the BQ25790 as well as the BQ25792. They're very similar devices and implement the same I2C configuration. But our PD controller also integrates support for the BQ25713 and BQ25731. So if the battery charging characteristics of the 790 or 792 do not meet your system's needs, this PD plus BQ implementation can be extended to these other 2 battery chargers as well. So closing out, tying this back to what we started this discussion with, the new PD 3.1 EPR voltage ranges. When it comes to the future of Type-C, PD plus battery chargers, PD 3.1 is definitely a part of that future. And TI, we're currently designing and evaluating a PD 3.0 EPR solution that pairs our next generation PD controller with the next generation battery charger. And if you are interested in this type of solution, you can learn more by following this link, as well as reaching out to your local TI representative. Okay, thank you very much.